Hello, everybody. My name is Robert Atkins, and I'm a rising senior computer engineering major at Hampton University. And my group mates are Biel Johnson, who is a rising senior electrical engineer at Morgan State, and Sierra Johnson, who is also a rising senior electrical engineer major at Morgan State, and Jason Burdick, who is a teacher at Sale High School in Tallahassee. And our project name is Hardware and Implementation of Computer Vision Algorithms for Smart Cars. So computer vision is a field of study on the problem of helping computers succeed. We want to reproduce these human capabilities inside of a computer. So our overall project objectives were to build a hardware platform for investigating computer vision algorithms in a driving simulator research environment, understanding AI, ML, deep learning, and computer vision concepts in self-driving cars, and implement efficient object detection algorithms and hardware. And my group mate, Brielle Johnson, will go over our project goals.
Our project goals can be broken down into 4 phases. In phase 1, we assembled our hardware. This summer, we constructed the Google AI Vision Cube and then verified its performance. In phase 2, we implemented an object detection algorithm successfully in Python environments, which leads me to phase 3. Unfortunately, time did not permit for phase 3 and 4. However, we aim to integrate hardware and software. The object detection model would then be placed onto the AI cube. In phase 4, I want you to look at the diagram below. The KITTI dataset is a compilation of images which will be used to train, test, and deploy models, which will then generate results so we can analyze the algorithm performance metrics. Here's an introduction into object detection. Object detection algorithms will recognize and locate objects with areas of interest selected based on the algorithm. 2 ways these are performed. Object detection using machine learning. Machine learning explicitly is coded because it's a manual selection. To name a few is aggregate channel feature ACF, SVM, and the Viola-Jones algorithm for human face and upper body detection. Object detection using deep learning. This one is not as explicitly coded like machine learning because the algorithms will learn from the data, which is why it's automated. And to name a few again, convolutional neural networks, regional convolutional neural networks, and you only look once, YOLO.
Methodology. There are 4 steps in the methodology phase. The first step was to build the AI Vision Cube and to go on the AI website to do the tutorials in order to get familiar with the hardware. The second step was to research our different object detection algorithms and to successfully implement them in Python. The third step was to develop a TensorFlow model of our object detection algorithm. And step 4 was to customize AOI using the KITTI dataset. And next I will explain my algorithm, the Viola-Jones. The Viola-Jones is an object detection framework to detect faces in real time. There are 4 steps in this object detection algorithm. The first one is hard features, in which the algorithm looks for specific characteristics such as the eyes, nose, and mouth to determine if it's looking at a face. The second step is integral image, in which the algorithm calculates the pixel value in the image to determine if determine a certain feature. The third step is attribute training. In this step, you're pretty much training the algorithm to rule out faces versus non-faces by feeding it different features. And then the fourth step is cascading. So what you're doing here is just seeing if the strongest feature is present in the sum window. If it's not, discard it. If it is, then keep looking to see if the second best feature is in the sub window. And now my partner Brielle will talk about YOLO.
Now let's take out YOLO. You only look once. V3 algorithm. It is a state-of-the-art object detection algorithm. It is capable to process up to 45 frames per second. However, it does have a drawback. This limitation is due to its difficulty with processing image containing small objects. To outline this object detection process, a raw image will be divided into grid. And then if you refer to the image below, you can see there's an image overlaid with a grid. And then there are two center images. The image above depicts bounding boxes, which are the areas of interest. And then below, you can see the class probability map, which would denote the class in which the final object detection is. In the image being the dog, the bicycle, and the vehicle. I'm going to pass the presentation off to my partner, Robert.
Okay, this next algorithm is called RCN, Region Convolutional Neural Networks. So the first thing it does, it takes region proposals of the image. Region proposals are just smaller parts of the original image that we could think could contain the objects we are searching for. And the next step, we take each region proposal and we'll create a future vector representing this image in a much smaller dimension using a convolutional neural network. We created future vectors from the image proposals. Now we will need to classify those future vectors. We want to detect what class of object those future vectors represent. For this, we use an SVM classificator. And so the cons of this algorithm is it takes a lot of time to train the network. It cannot be implemented in real time. And lastly, the selective search part of the algorithm, there's no learning at this stage, and this could possibly lead to bad candidate region proposals. All right, next slide, please. Okay, so our results, we got our Google AI kit constructed, and that's a picture of it. And the picture to the right is the actual RCN algorithm, the output of the region proposal stage. So as you see, the original image is on the left, and then the right, that's the regions, is taking the regions from that image. And it's a lot of regions, as you can see. And then a picture on the bottom is the final output from the RCN algorithm. This data set was airplanes, so we wanted to take an airplane, so we'll put bounding boxes around the airplane. And this is basically what we wanted. So that's the overall goal of this algorithm, was to put bounding boxes around the objects we are trying to detect. And the next slide, Sierra Johnson will go over our demonstrations.
So for our first demonstration is a joy detector. So if I smile, it turns yellow, and if it's blue, it means I'm frowning. Okay, and for our second video, it was a demonstration using my phone, detect live facial detection using my phone. So what I'm doing right now is that I'm doing a live facial detection with the Google AI Vision Kit app with my phone. So I'm able to detect live faces on my phone. And as you see in the top left corner, it shows the faces, which is detecting is 1. And now I'll be turning it over to Mr. Jason to talk about his RT lessons and activities.
The Google Vision Kit is a breakthrough technology. Its $100 price tag gives access to a computer, camera, Wi-Fi, Bluetooth, HDMI, and 4 GPIO pins. Compare this to Amazon's Deep Lens, which has a price tag of around $250 and requires internet and a subscription plan. This device has a way better opening price. The vision processing on the kit happens on the Vision Bonnet, which is attached to a Pi hat on top of a Raspberry Pi Zero. Training the mobile net requires feeding lots of images into Google's cloud computing supercomputers, and then freezing the tensor graph and downloading onto the kit where it runs offline. This feature allows Google's mobile net to be retrained, where you have to only retrain the upper layers of the model, leveraging on lots of previous knowledge and learning. Control of the kit is through the Raspberry Pi using a Linux operating system and uses Python to program. We, next slide. We tackled this project using the engineering design process. As a high school teacher, there are a lot of concerns about going back to school this fall during the pandemic. To address this, we targeted the front office secretary position as a great application to improve social distancing. We made prototypes, wrote code, tested systems, and finally arrived at a solution of Mike Wozniak, just because it was a one-eyed monster that had the same ideas like fitting the one camera in its eye. We attached electronics, servos, and we were able to give it more power to run all the systems. Testing is still underway, but on the next slide, you'll see his current progress of where he's at right now. This is my Mike Wozniak project. It's going to use some artificial intelligent vision systems and hopefully do some interaction here. When I come on screen, you should recognize me. So hey Mike, how you doing? Mike?
Hey, good evening, how are you? Oh, nice to see you. I tell you, it's great to be here in your room. Wait.
Thanks, Mike. And next thing you'll do, Mike, will you raise your hand? Put that hand down. Up. Down. So just looking at my smile. And Mike, we've had a good time today. Thanks so much for hanging out. I'll see you later.
Hey, thanks a lot. I'll be here all week. Remember to tip your waitresses.
Bye, guys. All right. So again, he's capable of doing lots more things, but that was just what we were able to accomplish in the last 4 weeks. In summary, through the phases of construction, during the first phase, we built the vision kits, tested demo programs, were able to run all the demo code. We had lots of problems through mobile devices or interfacing with different operating systems. We had problems with cables, SD cards, power issues. Some of these problems were met and tackled. Others we still need to address. The distance learning situation did make it difficult to obtain some needed parts and help troubleshooting each other was also an added challenge through Zoom. During phase 2, we were given our initial algorithms and each participant worked on researching and implementing their own code on Jupyter notebooks. We had varied success. Of course, the RCN model was the most successful, leading to edge detection and object bounding boxes. But problems did arise with the other models and we're still working on them. Google's MobileNet did work right out of the box with the Vision Kit, but we did not retrain it. So that's still a thing we'd like to accomplish. During phase 3, we still need to keep working. We've pieced some of the pieces together, integrating the software and the hardware into Mike Wozniak's project, but lots more testing and feature expansion, of course, possible. In phase 4, we're testing the Kitty framework we have not implemented yet. Next slide. These are our references that we use throughout our research and writing our paper. And then in the summary, or in our appendix, we do have the code segments from the Viola Jones and from the Mike Wozniak project. Thank you all so much for taking your time and listening to us. It's been great, great experience. Thank you so much.